Hello everyone. This week's lecture will cover Module 14. We will discuss aldehydes and ketones. Aldehydes are a class of organic compounds that contain the functional group CHO. Ketones are a class of organic compounds that contain the functional group CO. Aldehydes and ketones belong to a group of organic compounds that have a carbonyl functional group, which is a C double bonded to O. In aldehydes, the carbonyl group is at the end of the compound. In ketones, the carbonyl group is between two carbon atoms or two alkyl or aryl groups. Aldehydes are useful as solvents and perfume ingredients and as intermediates in producing dyes and pharmaceuticals. You may be familiar with the simplest aldehyde called formaldehyde, which is used in the preservation of biological specimens. Ketones are widely used as solvents, especially in the manufacture of lacquers, paints, and textiles. They are also used in tanning, as preservatives, and in hydraulic fluids. You may be familiar with acetone, which is used in removing nail polish. Aldehydes play significant roles in our daily lives. Traces of many aldehydes are found in essential oils and often contribute to their favorable odors. Aldehydes are not commonly found in several of the natural building blocks that create biological organisms, which include amino acids, nucleic acids, and lipids. However, most sugars, such as glucose, are derivatives of aldehydes. You may be familiar with the scent of vanilla, cinnamon bark, and bitter almonds. All the compounds responsible for these unique aromas and flavors are aldehydes. Vanillin is found in vanilla bean, and cinnamaldehyde is found in cinnamon bark. Ketones do not just have significant uses in our daily lives. They also have important physiological properties. They are found in several sugars and in compounds for medicinal use and natural and synthetic steroid hormones. For example, cortisone, an anti-inflammatory agent, has 3 ketone groups. In plants, camphor from the stem of the camphor tree, S-carvone from caraway seeds, 2-heptanone from blue cheese, and Z-jasmone, which gives the jasmine flower its unique scent, are all ketone compounds. Here are some chemical and physical properties of aldehydes and ketones. In terms of boiling point, for compounds of comparable molecular weight, aldehydes and ketones have higher boiling points than alkanes and ethers, but lower boiling points than alcohols and carboxylic acids. In terms of water solubility, aldehydes and ketones, like ethers, can function as hydrogen bond acceptors. Thus, smaller compounds have significant water solubility. Aldehydes and ketones are more polar. Thus, they have higher boiling point than comparable alkanes or ethers. On the other hand, they cannot form hydrogen bonds with each other, so they have lower boiling points than comparable alcohols. For instance, butane, an alkane, has a boiling point of 0 degrees Celsius, and it is insoluble in water. Propanol, an aldehyde, has a boiling point of 49 degrees Celsius, and it is soluble in water. Acetone, a ketone, has a boiling point of 56 degrees Celsius, and it is also soluble in water. 1-propanol, an alcohol, has a boiling point of 97 degrees Celsius, and it is soluble in water. Aldehydes and ketones are good solvents for alcohols because the lone pair of electrons on the oxygen atom of the carbonyl group can accept a hydrogen bond from the OH of alcohols. This lone pair of electrons also makes small aldehydes and ketones miscible in water. An example of this hydrogen bonding is shown for acetaldehyde and acetone. The stem names of aldehydes and ketones are derived from those of the parent alkanes or alkenes as determined by the LCC that contains the functional group. For aldehydes, we simply replace the last letter E with the suffix -al. For example, methanal is the IUPAC name for formaldehyde, and ethanal is the name for acetaldehyde. For ketones, we replace the E with -one. We indicate the position of the carbonyl carbon with a number. Propanone is the IUPAC name for acetone, and butanone is the name for ethyl-methyl ketone. Here are some examples of simple aldehydes and ketones. On the upper left, we have an aldehyde. For aldehydes, the carbonyl carbon is always located at either end of a straight chain compound. Thus, it is not necessary to indicate this position with the number 1 in the name. This compound is a 4-carbon aldehyde named butanal or butyraldehyde. The next compound on the lower left is a ketone. For ketones, we need to indicate the location of the carbonyl group. In this case, C2 is double bonded to oxygen, so we name this compound as 2-hexanone or hexan 2-one. The next compound on the upper right is a benzene ring with an aldehyde group. This type of aldehyde is simply called benzaldehyde. The last compound is a cyclic ketone. We name it as we would cyclic alkanes, but we replace the E with -one, so we call it cyclohexanone. To indicate the position of a substituent on an aldehyde, the carbonyl carbon is always assigned the number 1. This aldehyde is a 5-carbon compound with a methyl substituent in C3, so we name it 3-methylpentanal. To indicate the position of a substituent on a ketone, number the chain in the manner that gives the carbonyl carbon the lowest possible number. This compound is a 5-carbon ketone. Numbering is from right to left because it gives the carbonyl carbon the lowest number possible, which is 2. The substituent is a methyl attached to C4, so the name of this compound is 4-methyl-2-pentanone. Now let's try naming these ketones. In our first ketone, the first thing we have to do is find the LCC. Our LCC must include the functional group, which is this carbonyl group C-double-bond-O. So, we number our carbons from right to left to give our carbonyl group the lowest number possible. So, this ketone has 4 carbons and 1 substituent. A 4-carbon ketone is called butanone. The carbonyl group is in C2, so we include the number here. The substituent is a one-carbon compound called methyl. Methyl is attached to C3. So we write methyl and the number 3. So the name of this compound is 3-methyl-2-butanone. Now let's go to our next compound. As with the first, we need to find the LCC, and the LCC must include the carbonyl group. In this case, since it is at the center, we can number left to right or right to left. Let's go with left to right. 1, 2, 3, 4, 5. So, a 5-carbon ketone is pentanone. The carbonyl group is in C3, so we attach that number here. Now this compound has two substituents, one methyl here and another methyl here. So we write here methyl. Since there are two, we use the prefix di. And we include the carbon numbers to which they are attached, which is carbon 2 and 4. So the full name of this ketone is 2,4-dimethyl-3-pentanone. The naming of organic compounds follows a hierarchy when a compound contains at least two functional groups. The functional group that has the highest priority should be part of the LCC and becomes the parent chain name of the compound. Functional groups that have lower priority become substituents or side chains. Taking together all the functional groups we have learned so far in this course, the following order of priority is followed when naming organic compounds. As part of the LCC, the priority from highest to lowest is aldehydes, ketones, alcohols, alkenes, alkynes, and alkanes. As substituents, the order of priority from highest to lowest is alkyl groups, alkoxy groups, and halides. Aldehydes and ketones are not the highest priority functional groups among all functional groups in organic chemistry. As such, they can also become substituents or have lower priorities than other functional groups. When a ketone has lower priority, it becomes a substituent and takes on the prefix oxo. When an aldehyde has lower priority, it takes on the prefix formyl. Aldehydes have higher priority over ketones. So when both functional groups are in the same compound, we indicate the presence of the ketone by using oxo before the parent name. In this case, this compound is called 3-methyl-4-oxopentanal. Carboxylic acids have higher priority over aldehydes. So when both functional groups are in the same compound, the aldehyde becomes a substituent, and we indicate its presence using the prefix formyl. This compound is a benzene ring with a carboxylic acid attached and an aldehyde as a substituent. So we name it 3-formyl benzoic acid. Now let's practice naming these two compounds. For the first compound, our first step is to identify all functional groups present. In this case, we have an aldehyde here and a ketone here. Since aldehydes have higher priority over ketones, our LCC must contain the aldehyde and the carbonyl carbon becomes C1. So numbering is from right to left. This is 1, 2, 3, 4, 5. Our LCC has 5 carbons. A 5-carbon aldehyde is called pentanal. The ketone becomes a substituent, so we indicate this by attaching the prefix OXO and the carbon number to which it is attached. So we write here OXO and the number 4. Now let's go to the other substituents present in the compound. There are 2 alkyl groups here, a methyl attached to carbon 2 and another methyl attached to carbon 3. So we write this as methyl, and since there are 2 of them, we use the prefix di and we indicate the carbon number to which they are attached, which are 2 and 3. So the full name of this compound is 2,3-dimethyl-4-oxopentanal. Now let's go to the other compound. This compound has an alcohol functional group here and a ketone here. Ketones have higher priority over alcohols, so the ketone must be part of the LCC and should get the lowest number possible. So our numbering should be from left to right. This means this is carbon 1, 2, 3, and 4. Note that we don't number this as carbon 4 because our LCC must also include the substituent that has higher priority over this alkyl. So our LCC has 4 carbons. A 4-carbon ketone is called butanone. And the carbonyl group is attached to C2. So we indicate that with a number 2 here. Since the alcohol is a substituent, we change its name to hydroxy. The other substituent is methyl. When writing substituents, we arrange them alphabetically and include the carbon number to which they are attached. So in this case, we first write methyl attached to carbon 3, then we write hydroxy attached to carbon 4. So the full name of this compound is 4-hydroxy-3-methyl-2-butanone. Aldehydes and ketones can also exist as cyclic compounds. When an aldehyde is part of a cyclic compound, we name the compound using the suffix carbaldehyde. For cyclic ketones, the carbonyl carbon is assigned the number 1. In our first compound, we have a cycloalkene with 5 carbons. The carbonyl group is assigned number 1 and the double bond is given the next lowest number, which is 2. So the name of this compound is 2-cyclopentene carbaldehyde. This next compound is a cyclic ketone with a bromine substituent. The carbonyl carbon is assigned number 1 and bromine is assigned the next lowest possible number. So the name of this cyclic compound is 2-bromocyclohexanone. Now let's try naming this cyclic compound. this cyclic alkane has 1, 2, 3, 4, 5, 6 carbons. A 6-carbon cycloalkane is called cyclohexane. Our cyclohexane has two substituents, the aldehyde functional group here and an alkyl here. So when numbering, we give highest priority to the aldehyde over the alkene. So this is 1, 2, 3, 4, 5, 6. When an aldehyde is part of a cyclic compound, we change its name to carbaldehyde. So we write carbaldehyde. Then we write the name of the other substituent, methyl, and include the carbon number to which it is attached. So the full name of this compound is 3-methyl cyclohexane 1-carbaldehyde. Our next compound is also a cycloalkane with 1, 2, 3, 4, 5 carbons. A 5-carbon cycloalkane is called cyclopentane. The cyclopentane has 3 substituents, a ketone here, and a methyl here. So when we number the substituents, we number it giving highest priority to the ketone over the alkyl. So this is carbon 1, 2, 3, 4, and 5. Since there are 2 ketone groups, we indicate this using the prefix di. So we write cyclopentane dione. Then we indicate the carbon to which the oxygen is attached, which is C1 and C2. Then we add the other substituent, methyl, and the carbon to which it is attached, 3. So the complete name of this compound is 3-methyl 1,2-cyclopentane dione. Aldehydes and ketones also have common names. Ketones are named as alkyl attachments to the carbonyl group plus the word ketone. We use Greek letters instead of numbers to indicate the location of substituents on the attachments. Here we have 2 ketone compounds. We can name these compounds in the same way we did for ethers. That is, we name the attachments on both sides of the carbonyl group separately first, then join them alphabetically. In the compound on the left, the alkyl on the left side of the carbonyl group has 3 carbons, so we name it isopropyl. The alkyl on the right side is methyl, so the common name of this ketone is methyl isopropyl ketone. Its IUPAC name is 3-methyl-2-butanone. Note that we do not consider the iso in isopropyl in the alphabetical arrangement of the attachments. In the next compound, we have an ethyl attachment with a bromo substituent on the left side of the carbonyl group, and we indicate the location of the bromo substituent using the Greek letter alpha. The attachment on the right side is isopropyl. So, the name of this ketone is alpha bromoethyl isopropyl ketone. Its IUPAC name is 2-bromo-4-methyl-3-pentanone. Here are examples of ketones that are more widely known by their historical common names. We have acetone, acetophenone, and benzophenone. For aldehydes, the stems for the common names of the first four aldehydes are as follows. A 1-carbon atom aldehyde uses the prefix form. A 2-carbon aldehyde uses acet. 3-carbon aldehyde uses propion. And a 4-carbon aldehyde uses butyr. We use the common name of the acid, we drop the ic acid, and add aldehyde. For example, the 1-carbon formic acid is also known as formaldehyde. The 2-carbon acetic acid is also known as acetaldehyde. A 3-carbon propionic acid is propionaldehyde. And the 4-carbon butyric acid is butyraldehyde. Aldehydes are formed from the oxidation of primary alcohols. Primary alcohols can be oxidized to aldehydes by an oxidizing agent such as an aqueous solution of acidified potassium dichromate. This reaction is summarized as follows. RCH2OH plus O gives us RCHO plus H2O. An example of this oxidation reaction is the reaction of propanol with oxygen, which results in the formation of propanal plus water. Ketones are formed from the oxidation of secondary alcohols. Secondary alcohols can be oxidized to ketones by an oxidizing agent such as an aqueous solution of acidified potassium dichromate. This reaction is summarized as follows. RCH2OH plus O gives us RCHO plus H2O. An example of this oxidation reaction is the reaction of 2-propanol with oxygen, which results in the formation of propanone plus water. On the other hand, aldehydes and ketones can be reduced by a reducing agent such as sodium borohydride to form alcohols. When the symbol equation is written, the reducing agent is represented by H in brackets. Aldehydes are reduced to primary alcohols as summarized by the chemical reaction RCHO plus 2H yields RCH2OH. Ketones are reduced to secondary alcohols as summarized by the reaction R1CHOR2 plus H yields R1CHOHR2. The reduction of propanal to propanol is the reverse of the oxidation of propanol to propanal. The reduction of propanone to 2-propanol is the reverse of the oxidation of 2-propanol to propanone. And that's it for our lecture on aldehydes and ketones. In this lecture, we learned that aldehydes are derivatives of hydrocarbons with a CHO functional group. Ketones are derivatives of hydrocarbons with a CO functional group. Aldehydes are named using the suffix -al, whereas ketones are named using the suffix -on. Aldehydes and ketones have common names, and aldehydes and ketones are formed from the oxidation of alcohols, whereas the reduction of aldehydes and ketones form alcohols. And that ends Module 14. Modules 13 and 14 will have a combined activity worksheet. Please refer to Module 14 for the activity instructions. Thank you for listening.